So let me give you the combinatorial definition, and then I'll say a few words about why we care about tree codes. But what's a tree code? So you look at the binary, like the infinite binary tree. It's actually easier to work with infinites here. If it's linear. And what you do is so it's infinite. So you're going to assign a color to the edges. Actually, check them just a second. So maybe you're going to use free colors or whatever. You want to use as few as colors as possible, as I say, but you assign colors to all edges. And you want that, despite the fact that the number of colors is small, hopefully 4, the tree is kind of colorful. And in what sense? So I'm taking a step back and I'm looking at the entire infinite tree. And I'm looking at, so the thing I want is the following. I want that if you take any two nodes at the same depth, so maybe that depth is some h, and you kind of trace back to the least common ancestor, and the first time they meet when you go up to the root, then I want that if you compare this sequence of nodes, like this is the first color, second color, fourth color, with that, you get high distance, high Hamming distance, many disagreements. So I want that for many of the corresponding pairs of edges, I mean, this is bad. You got the same color. But this one, you're going to get one for your, like this.
So the trees, is the tree necessarily full?
Yes. It's full and it's infinite. Complete infinite. Yes. So that's what you want. You want that for any u of v in the tree of equal depth. You want that the number, so you want that so if you call it uv and you call this w, the w is the least common ancestor, then you want that the color string from w to u and the color string, I'm expecting forward here, again in the notes is written perfectly because it's actually copied from input. We want that these two color strings have a Hamming distance, should give some Hamming distance. Okay, now we need to figure a parameter, so let's call it delta, times the length. So relative Hamming distance delta. So there's a fraction of the pairs disagree. Like in a code, but in this weird fashion. So you want an infinite tree, you want to color the infinite tree.
The delta is.
You should think with the concept with 0 and 1.
Yeah, it could be 1.
Could be
the
1.
Distance to be like if you take two vertices that are the same depth and the left balance.
Yes, good.
It would be relative to
Right, sorry. So this is the UV, you're right, and the distance of the code is the infinite. So the minimum, but it's infinite set.
I meant that if you might take. Never mind. Maybe.
And what is the goal?
Good. So is it?
Yeah.
Delta UV is like normalized by the length.
Right, exactly. So if the length here is like L, then it's the number of disagreements divided by L. So it's fair. Two siblings should just be distinct. The color should be distinct. But if the W is far away, then you have more. You require more in terms of how many disagreements you have, but compared to the disagreements you can have. And you see, it does count this, but that's not fair. I mean, this will always be the same. So you count only from where it counts. And the goal, like before just saying something about the goal, let me just say what motivation for this and then it will be clear. So the motivation is like in coding theory, but it's not called interactive coding. So in interactive coding theory, which invented in 1994, is so instead of me sending you a message and then you are happy if you got it right or not, we're actually conversing. So I'm sending you a bit, you send me a bit, it's 2 bits, maybe we play chess or something, right? There is a conversation going on, not something more dynamic. And what I see determines what I'm going to tell you. And it's kind of complicated because if I didn't understand you, I say something which is unrelated, you hear me say there is like, there's a point there, you can't put something. So you want to be able to have interaction over imperfect channels, not just sending a message. And if you think about it for a while, code doesn't help you. There is no good reduction from this combinatorial object code for this problem.
Probably there's no.
Well, if the reduction just construct the tree code, right? So there is no. It's not the same problem. It's just a different nature. Right? So what Leonard Schulman did in sequence of paper is he noticed that if you have this object which you introduced, you will be able to obtain an interactive kind of protocol that works even if there are noise on the channel. And I'm going to lie in what I'm saying now, but it's a good intuition. So the intuition is it doesn't work this way. The reduction to codes, the reduction, the way you use tree codes in this interactive protocols is more complicated, but the intuition is the following. So this is me and this is you. And kind of this is the last time we understood each other. Right? So I'm sending you, I want to send you bits. So when I move left, I want to send you 0. When I move right, I want to send you 1. But instead of that, I'm going to send you the color that I see. That's kind of what's going on. And maybe we kind of understood each other so far, and here we kind of diverge, and we don't talk about the same thing. But what you can do, it's not what you do, but what you can do to give intuition is, well, from time to time, I just pause and see if we are on the same page. So we are going to sample an index, maybe in powers of 2, but you're going to sample an index and just ask yourself, were we okay on that part of the talk or not? And if there are many disagreements, we'll be able to kind of capture this. That's kind of the idea. It's not more, it's more complicated, but that's the general.
So the goal is the highest delta possible?
Exactly.
Okay.
So you just want the highest delta possible because that gives you the probability that you catch it. But you also want to use a few columns because this determines the rate. Because I wanted to send a bit moving left to right and I send a column number. So if I'm using 8 colors, it's going to be a rate of 1/3 because I'm sending 3 bits per bit. So it's kind of the same thing. You want good rate distance trade-off, but the rate and distance are not exactly what they want. The rate is how many bits you send per bits you wanted to send. There's also additional things you send back and forth to verify things more complicated.
So like the further the conversation is, it's harder to catch disagreements.
Right, the way I described it. Yes.
And is there
But
is there some way to fix the disagreements, or is this just to catch them?
No, good. So there are protocols that just deterministically and 100%, because there is no randomness, they actually manage to find the last point in which we agree, and we kind of reroute or redo everything we did and continue from here. So there is a way to use the trigger to actually do a deterministic interaction, but it's slightly complicated.
And just to make sure we have control of the construction of the tree.
If you have a tree, okay. So if you have a tree code, when there is, it takes like 6 hours to move and show it, an algorithm that uses the tree code and to obtain an interactive coding scheme. You need to actually define what it is, right? But you need the tree. Assuming that both sides have the tree, you can do it.
The tree with specific delta.
Good. So as long as delta is like
Not 0.
right, you're happy. Non-zero is good because it's infinite, so it's either 0 or not. If it's any number, then it's a number. But you want delta to be large. I mean, it's better to have it large. But again, there's also the question of how many colors you use, so you want the treasure. That's it. I think it's a really cool problem. I mean, what's the problem? Trying to construct the trees. So it's a good problem. And let me tell you, it's late. So let me tell you the easy stuff. And next week, we're going to actually do something more deeper.
Only 2.
No, like in terms of how many hours you have to listen to this. For me, it's like midnight. I need to go to the gym today because it's worse than going to the gym. Okay, so let's calibrate our expectations. And let's prove that we cannot have a tree code Well, delta is 0, you can go with, and one delta which is not 0. So we cannot have a tree code that uses two columns. Just to make sure we understand the definition. So here there are fact. There are no tree codes with delta larger than 0, of course, and C is down of column, okay? C equals 2. It's too much. I mean, it's too little. So can you see why? It's not so hard. Let me just start. So let me just start the several ways of doing that. So first of all, notice that if they are just as a side note, which will be important here, if two siblings, right, U and V are like have a common parent, like direct parent, have the same color here, the distance is 0. So you can't have that if you want distance at 0. So this means that from the root in particular, you have two colors. And then just continue like that, but maybe in like interesting ways. So that's actually not so
Due to symmetry, just
It
don't
can't be
do
interesting.
interesting
it
way.
can't be good.
Don't do interesting stuff. Just claim symmetry and keep.
Right, exactly. You can either do that, good, because who cares if it's like this or that, and then, but the other way of saying the same thing, which we scale to 3 colors, and I want to do 3 colors, that's all, is that you can just from here, I mean, let's say maybe if even from here, but you can from here, you can continue on the same color all the time, right? What you're saying is a better way of saying that, but it won't scale for 3 colors, so let me say it this way. So I'm going to take, I'm going to give you a sequence of U's and V's, right? So this is U1 and V1 exactly, and this is U2 and V2, and so forth. So I'm just going to take U1 and V1 are just the sums of the root, but from here on, I'm just going to go always on the blue. Say, you can make it more interesting if you want. You can go the blue, and what you see is that you get a sequence of pairs where the distance is 1 over is always like 1 non-normalized and 1 over L if L is the depth normalized. Right, so the distance or the relative distance between UL and VL is like 1 over L, but only the 1 out of the L mismatch, the first two. And the infinite therefore goes to 0. Good. 3 colors. You can't do 3 colors, I'm just telling you. But why? It's slightly border. I wanted to put it in the dance exam. And because it uses something that you see that. But then the
That
other
was the only requirement for questioning the exam.
right, you need to understand the trick stuff, I guess. But the other lecture will stop me because I talked for 15 minutes about what the trick is. So right, so why can't you do with 3 colors? Let me just draw the initial thing. So with 3 colors, I mean you can with 3 colors. So let's say sorry?
They don't know what's an infinite together.
It's wrong, right? So maybe you have that, you have 3 colors, right? So something like that. So what can you do? You want to do the same strategy. That's why I'm presenting the proof like that and not as you said. So what do you say? What do you know about these 4 edges? 4 edges, 3 colors.
2 of them have the same color.
Right, with the pigeonhole principle, which is the only thing we do that one. Here I can draw it less interesting than that. 4 edges, 3 colors, 2 of them will be the same color. If they're coming from the same vertex, you're done because you have 2 brothers with the same color. So actually, the interesting case is that they go like that: 1 from here and 1 from there.
Why, following your examples, why can we expect that for some finite?
Good question. Yes. Well, let's talk about it. It's a great question. Why shouldn't they be able to do that for any constant? Right. Good. So I'll talk about that, of course. But it is. But the idea is, this is going to be U1 and V1, so that we gain nothing. But from here on, we are gaining always. Because from here on, so what I'm going to do is use the edges with the same color and proceed like that. Now they have like 4 snap, 4 edges going out of them. So I can use, say, this, right? There's always a way to continue and get the same. No. 4 columns. What about 4 columns? Now you can do like 1 level analysis. So I try to do 2 level analysis.
Oh, it doesn't work.
Sorry?
It doesn't work?
It doesn't work. There are triggers with 4 columns. Not really. So 4 is enough to answer the question. Then spend like a couple of days trying to.
I think I know why.
Okay. Tell me.
I think it relates like, because we are looking always like on one level and the next one for the color. So like 4 is when we have 4 colors, it's like a kind of, if we want to make a maneuver to make it not work, we always get stuck because like we got the 2 ones and then like 4.
Right. So that's like an intuition for why you, but you can, I don't know if you can make it into a construction, an argument it gives. This is why it's hard to prove things in possibility like that, but it's not why it's possible. But anyhow, there are 4 color records. And the distance is also not that terrible. The best we could do is like this one.
When will they start getting repetitive, like the 4 color tree codes?
So good. So there is a good repetitive and bad. There is no bad repetitive in the sense that distance is still good, but yeah, you get the same patterns, but not in a way that stops you from getting distance. So we don't know how to find those. I don't know how they do, but they exist. They don't right. So
Wait, nobody knows or?
nobody.
Ah.
To the best of my knowledge, maybe someone now nights on. Generally, nobody knows. But that's also the thermal distance. The best you can do is like 1/4 with 4 columns.
How do you know the distance without knowing the tree itself?
The probabilistic method. Good. So, so what you do to do that is you use the probabilistic method, which again always laughs at your face. It doesn't give you, it's like a zero knowledge proof. It gives you no information about it. But it gives you the construction. This is not it's like an irrational number. It's a root of some polynomial that you figure out and analyze this. But it exists. Next time, actually, this appears as is in the notes, but I just copied it from the paper. But we'll prove maybe not 4 colors, but maybe like 20 colors exist for some distance. But let me tell you something about constructions. So this is what we're shooting for. I mean, for me, I don't really care about the distance. As long as it's constant, I'm happy. But I want as few colors as possible. Later, when we understand tree codes, we'll try to have a better trade-off between the 2 parameters. This is not where we are.
No.
Okay. So construction. So this is the probabilistic method. It's not a trivial proof of the probabilistic method. Not at all, because where did it fail? Just before the constructions. If you just, possibly you can't say what you're going to say. It makes sense. If you take the uniform distribution over all colors, which is not possible, it's an infinite set, but if you take that, then 2 siblings will have the same, will fail, right? With probability 1 over the number of colors, right? And you have many siblings, so you can't union bound. You have like infinitely many siblings, you can't union bound. So you somehow, when you do that, and you'll do it next time, you somehow need to make sure that, okay, you use randomness, but you use also the structure of the problem. You inject the structure to the randomness, vice versa. Because what we will do is we'll make sure that we'll have some randomness, but we'll make sure that these 2 are the same, if and only if all siblings are the same. 2 siblings are the same, if and only if all siblings are the same. We'll make sure that the coloring is such that it respects the tree structure. And that will be a good step, because you don't have to worry about siblings on it. But that's later. That's slightly kind of technical, a little bit. We'll actually show 2 proofs for that, because I want to show you like first of all, one example where we use the probabilistic method, like easy stuff on probability, but use the structure of the problem together with probabilistic argument. And we also prove it using the Lovash local lemma, which maybe some of you seen. I explain it for it. I won't prove it, I explain. And that's like a non-trivial, deep but non-trivial tool from probability theory that enables to prove something about, you don't have, it allows you to say something about cases where you have dependencies between the events, but you can control. So for example, siblings, right? This sibling may depend on that sibling, but siblings are, like, they're actually completely uncorrelated. But if you look at like maybe not siblings, but two vertices of distance 2 from the least common ancestor, when there are only few that kind of intersect. And you can use that. There are not too many things that depend on you, kind of control over the dependencies using the Lovash local lemma. It's a central tool, so we need to see. So we are going to show 2 proofs for that. But just for fun, let me spend the next 10 minutes about what we know about construction. Let's what? Constructions. Okay, I'm not going to
Like explicit.
explicit construction, like when I say construction, I essentially mean it. And when I say, at some point I will define what it means. But in this case, it means like that if you want to know what the color of an edge, well, the description of an edge is the way to that edge, right? So if it's a depth n, you specify n bits for me. So I'm going to run poly n time and tell you the edge. That's because it's infinite, you can do better. It's kind of the same thing as just printing the tree like that. It's even better. Because you do that locally. Okay, construction. So let me just say there is an easy construction. It's actually a funny story. So okay, so the trivial, before the easy, there is a trivial construction. This is easy. So first of all, what am I saying? I say we don't know how to do it, so I'm constructing. So let's relax the problem. And now let allow ourselves to use a number of colors that depends on the depth. So increase the number of colors with time. But not too much. Hopefully it will stay 4. Okay, that's a good, that's something that's actually good. Allows you to make some progress. So if I'm using 2 to the n colors, it's like super trivial. And it's the depth. Because I can just, what can I do?
New one.
Right, exactly. I just encode, I can just, the color will be the address on that edge in the tree. You have n bits when you have 2 to the n colors, you can do. That's trivial, distance is 1, z is unique. It's clear. So the easy thing is to do it with poly n. Say this delta is constant, with poly n number of colors. You can make, you can do it for any distance and the poly will just be larger as delta goes to 1, but it doesn't matter. And that's funny actually, because it's not even a paper, it's a, so Schulman invented this. So people just kept asking him, just said that it's easy in the paper. And people asked him, how to do that? And then he put a note, like he didn't even put a note, just probably the email he sent on the web page. And you cannot, it's impossible to understand what's there. But there is just, if you just don't do that and think of it yourself, it's easy. But you don't get what's here. I don't know what, I'm not sure if it's the same thing. Ask them. It says, yeah, it's on the same. So when I put it in a homework question, by the way, of course, a couple of years ago, I said the easy question is just to do it, and the hard question is just to understand what he did. And not the hard one. But it's not hard. And there is so the best we know how to do today is polylogging.
That's the best.
Yes. The best now we know slightly something that's slightly better.
So there's no constant colors that is
No. So what we actually know really, to be more precise, is like a log n to the delta number of colors.
for any delta.
Maybe delta square root, and there's an O. Like for any delta. So if delta is like constant, it's polylog n, but it's maybe a small polylog, it's like this one. And if on the other end you can stretch it all the way. So if delta is like 1 over log n squared, which makes this a constant, and if delta is the order of delta of 1 over log n squared, so it's not a constant distance, but you know it's not such so bad. Then you can get constant number of poles. So you can say you actually do know how to construct a tree with a constant number of poles, but the distance is not constant. It's like slowly vanishing. Not so bad. Like 1 over n is trivial. 1 over log n is not trivial.
Why is that constant?
If you plug it here, because the square will keep the square root, and you get 1 over log n, so log n to the 1 over log n is constant. Because k to the 1 over log k is constant. You get used to it at some point. Right. And let me tell you one thing about this theorem. Just one lemma that's used there. Again, it's all very informal. I'm just telling you things. Okay, so it turns out that the way to obtain that, not quite that, but something in polynomials. What you do is there's only one thing you can do. There is a read Solomon code. There's no other code. There's expanded codes. They are not suited here. So there are no other codes. So if you want to construct something which is, by the way, strictly stronger than the code, show that, then either you invent a new type of code, which is actually the right thing to do here, but maybe luck, or you just follow the giants, right? You read Solomon. But the problem with read Solomon is that it doesn't fit. Like it doesn't give you like in read Solomon, you're given the entire message, you form a polynomial and you evaluate it. Here, what happens really is if you formalize it carefully, you're getting the coefficients of the polynomial slowly. So you can't evaluate the polynomial once. Actually, it's not a polynomial, it's infinite sequence. It's a power sequence. So you need something else. And it turns out that a good basis for that is the Newton basis of polynomials. So what's the Newton basis? Again, everything is at a high level. So instead of using the ordinary basis, which everyone uses, which is fine, let's use the basis which is x choose 0, x choose 1, x choose 2, where this is the polynomial that you think it is. Like x times x minus 1 divided by 2. So you see, the that was really important. So the cool thing about this polynomial is that it's kind of dynamic or online with respect to the points 0, 1, 2, and so on. So for example, if you have a polynomial, so say I'm telling you, I care about the polynomial, so I want to look at the polynomial that goes through these points, and that interpolates through these points. Okay, so at 0 it's m0, at 1 it's m1, and so forth. So what is this polynomial? So you can do a Lagrange interpolation or whatever, get a polynomial. And when I tell you, well, sorry, I need one more point. Please, at t plus 1 go over n t plus 1. If you do an interpolation for this sequence, you get a polynomial which is typically completely different. All the coefficients will mess up in this basis. But in this basis, they won't. They will stay exactly as is. It's only the new coefficient that will change. Use it in numerical analysis, for example, because it's stable.
And that's why you encourage us to examine like the size of A plus A.
Maybe it's like a brilliant move, but no, that's maybe it's something. But anyhow, so what the dilemma that you need, if you look at this for a second and you say, okay, what can I do with this and so forth, you get to the following question about polynomials. So it's about the zeros of a sparse polynomial. You should be careful when we talk about sparse polynomials. So, okay, so next time I'll tell you, let's keep attention because there's one more minute, take 5. But next time I'll tell you that the analog of the replacement or the fundamental theorem of algebra you need here is something about the zeros of sparse polynomial. Sparse is basis dependent, so with respect to this basis, and okay, and then we'll continue. Don't want to stress it. See you next week.